All right, here is going to be the solutions for these exercises for this section. And for these, what I want you to remember is that you should be trying these on your own first until you're stuck. If you're stuck on one, you could always move on to another one. And if you want to get unstuck, you can use the video to see what I'm doing. Until you get unstuck, until you feel like you have an idea of what to do, then you should continue trying to do it on your own. Because just watching me do problems is not the way to learn to do math. It's something where you really have to practice doing it. It's sort of like just trying to learn Spanish just by listening to other people speak Spanish. It's not really going to work. You got to do it on your own too. Or it's like learning piano by watching other people play piano. It's not going to happen unless you're doing it. So after you get unstuck by getting some help from the video, then keep going on your own. And if you are able to do these yourself, then that's great. You can use the video to check your answers. If you get most of these answers, you can skip ahead in the video to see where the answers are. Okay, so with that in mind, let's get the change in x between these different points. Here, x is going up by 5. Here, it's going up by 5 again. It's going up by 5 each time. So the change in x is always 5. And then here, the change in y is 1. Here, the change in y is 2. Here, the change in y is 3. Here, the change in y is 4. Here, the change in y is 5. So if you get the change in y divided by the change in x, it will be 1 over 5. Is that equal to 2 over 5? No. Is that equal to 3 over 5? No. So it's not linear. Okay, let's look at this one. Here we have x going up by 5 at first, then goes from 5 to 15. That's going up by 10. We go from 15 to 30. That's going up by 15 now. So the change in x isn't always the same. Here the change in x is 25. So does that mean it's not linear? Well, not necessarily, because what it means to be linear is that the slope itself, the fraction, the change in y over the change in x, needs to be the same. So maybe that's the same. So the change in y here is 1. Here the change in y is 2. Here the change in y is 3. Here the change in y is 4. And here the change in y is 5. So the slope between the first 2 points would be 1 over 5. Is that equal to the slope between the second 2 points? That would be 2 over 10. And 2 over 10, that does reduce to 1 over 5. So those are the same. What about from x equals 15 to x equals 30 here? The change in y here is 3. The change in x is 15. Oh, 3 over 15, that also reduces to 1/5. So that one's good. Then the next one is 4 over 20. That reduces to 1/5, so we're good. Then we have, let's see, 5 over 25, which also reduces. So this is linear, and the slope is 1/5, or 0.2, if you want it as a decimal. Okay, so then, if we have the slope, we could use slope-intercept form, because we got the intercept right here. So you could write the equation as y equals that 10. Oh my gosh, my computer is being so annoying this morning. 10 plus 1/5, or 0.2, times x. Okay, so that's that one. Here's exercise 2. The table shows the debt, F, in billions of dollars, held by Fannie Mae, the government-sponsored mortgage institution, in year Y. So in 1988, that year, the debt that they owned was $105 billion worth of debt, meaning that people who have mortgages owe Fannie Mae $105 billion altogether. In 1990, it went up to $123 billion. So we're going to assume that the debt grew at a constant rate of change. So, okay, so what is that constant rate of change going to be? Well, it's going to be the change in F divided by the change in Y. And let's see, from here to here, the change in F is, we could do like F2 minus F1 to get 123 minus 105. Divide that by the change in the years, which is 1990 minus 1988, which gives you, let's see, 123 minus 105 is 18. So that gives you $18 billion. Divided by 2 years. So what that constant rate of change is going to be 18 divided by 2 is $9 billion per year. So the debt that they own, that people owe them basically, is increasing at a rate of $9 billion per year. So what that means is in 1989, it's going up by $9 billion, and it was $105 billion. So you can just do plus 9 times 1 year that went by, and that's going to give you $114 billion. And what about here? What is it going to be in 2000? Well, you could go from, let's actually just start here and go up. Well, how many years are going by? From 1990 to 2000, that's 10 years. And if it's going up by $9 billion per year, this could be plus 9 times 10, which would be plus 90. So 123 plus 90 would be $213 billion. Okay, so that's one way to do it. The other way is once you have the slope of it here, you can use point slope form. We could say we're going to do f equals f0 plus the slope times y minus y0. And the f0 you could use as 105, and the y0 could be 1988. The slope is $9 billion per year. So plugging all that in gives you this formula. And if you plug in y equals 1,989 into this, you can check that it will give you a result of 114. And if you plug in y equals 2,000 into this, you can check that it's going to give you a result of 213. So that's the other way to approach it. If you don't want to just like add the amount that the debt increases, you could do the same thing basically, but using this equation. Okay, so that's exercise 2. All right, so exercise 3, we have architects are designing a motel with 10,000 square feet of available space for rooms. It will have S small rooms, which are 250 square feet each, and L large rooms, which are 400 square feet each. Okay, so let's write an equation about S and L. Okay, so the trick here is that the space taken up by large rooms and small rooms together is going to be, well, let's see. If you have S small rooms and they're 250 square feet each, then you can do 250 times the number of small rooms. So that's the amount of space taken up by small rooms. Then the large rooms are 400 square feet each. So the amount of space taken up by large rooms is going to be 400 times L. So if L is 1, that gives you 400 square feet. If L is 2, that gives you 800 square feet. And then if you add that to the amount of space taken up by the small rooms, you get the total space taken up by rooms. And that is 10,000 square feet available for rooms. So that is your equation about S and L. Now let's find the S-intercept and the L-intercept. Okay, so let's say we want to find the, let's start with a outline of what this graph is going to look like. We'll get some axes here. Let's say this is the S-axis and this is the L-axis. And if you did this the other way, that's fine. It really doesn't matter. Now let's say we want to find the S-intercept. That's going to be a point somewhere on the S-axis here. Now where is it going to be? What's going to be that value of S? Well, whatever that value of S is, it's going to make the value of L there equal to 0, because being on the S-axis means you don't go up or down at all. So that's where L is equal to 0. So we want to plug in L equals 0 in this equation and see what S makes that true. So that's going to be 250 times S plus 400 times 0 equals 10,000. All right, so 400 times 0 is just 0, so this just gives you 250 times S. Unfortunately, my S's look like 5s, so sorry about that. But then we're going to divide both sides by 250 here to get S by itself. And 1,000 divided by 200, oh, this should be 10,000, excuse me. 10,000 divided by 250 is 40. So that means if L is 0, the value of S that we get is going to be 40. So there's this point here, 0, actually it should be 40, 0. All right, so that's going to be over here somewhere. That's the actual point that we have. All right, now let's do the same thing for the L-intercept. We need a little bit more room. The L-intercept is going to be a point on the L-axis, and we want to know where is that point on the L-axis. Is it up here? Is it down here? So that's going to be when S is 0 is the trick, because if it's on the L-axis, that means you don't go left or right at all. So that means the S is 0. So we're going to take that 0 and plug that in for S, which gives you 250 times 0 plus 400 L equals 10,000. And 250 times 0 is just 0, so this is the same as just 400 L equals 10,000, divide both sides by 400 to get L by itself. And 10,000 divided by 400 is 25. So this is the point where S is 0. The L is now 25. Is what makes that work. So that's going to be a point, I don't know, about here. And that means we can now graph the equation. It's going to look like this. Okay, so oops. That is the graph of that whole equation. Now let's look at part C. What do the intercepts tell you about the motel? Well, for the S-intercept, the 40, 0 that we got, that means that's the value of S is 40 when L is 0. In other words, if you build 0 large rooms, then the amount of small rooms you can build is 40. And likewise, the L-intercept, if the point Z, like S equals 0, L equals 25 is on the graph, that means that if you build 0 small rooms, then you have enough room for 25 large rooms. All right, so that is exercise 3. Let's look at exercise 4 here, where we have a mountain climber feels the air temperature decrease as his elevation increases. When the elevation is 200 feet above sea level, the temperature is 60 degrees Fahrenheit. And then the temperature decreases by 3 degrees Fahrenheit for every 1,000 feet the climber ascends, which means goes up. So let's use the given numbers to write a point slope form equation for the function t of h, which gives you the temperature at an elevation h feet above sea level. So I think just like I did with the examples 1 through 3 here, or at least with examples 1 and 2, it helps to make a table where you can see what are the values of the input and output of this function that you know. So that's what we're going to start with. So let's take a value of some values of h here and get some corresponding values of t of h. Okay, so we have, so h is the feet above sea level, the elevation. So if we know that if h is 2,000, then the temperature is 60 degrees Fahrenheit. So we've got that. What else do we know? If the climber ascends 1,000 feet, then that's going to take him or her to elevation of 3,000 feet. What is the temperature there going to be? It says, so after doing this 1,000 foot ascension, the temperature decreases by 3 degrees Fahrenheit. So it went from 60 degrees to 57 degrees Fahrenheit. And if they go up another 4,000 feet, up another 1,000 feet to 4,000 feet, then the temperature is going to go down, decrease 3 degrees more to 54 degrees Fahrenheit. So that's, as long as you understand the language here, then you should be able to make a table like this. So that's always a good first step. And once you have this table, that will help you in making sure that the formula that you get, the equation that you get, works. So let's see. Let's figure out the slope here. So here you have a delta T of -3 and a delta H of 1000. So if you want to get the change in temperature divided by the change in elevation, that would be -3 divided by 1000. And you could do that with a calculator, or you might just be able to do it. This is 0.003 degrees Fahrenheit per foot. So if the climber goes up just 1 foot, like climbs on a little rock, then the temperature there would go down by 0.003 degrees Fahrenheit. Okay, so let's see. So that's the slope, and you can use a point. We can say that there's this point, H0, T0, which is 2000 is the H value, and the T value there is 60. So you can write this in point slope form then, as T of H equals that T0 plus the slope times H minus H0. So this is the same point slope form from the beginning. And we have the values of T0 is 60, the M is -0.003, the H0 is 2000 feet. So I'm going to plug all that in here. So that should be the formula. Now here's where it really helps to have a little table for this kind of thing, because what you can do now is take these values of H and check that they work. If you plug in H equals 2000, then make sure that the result that you get is 60. If you plug in H equals 3000, make sure the result you get is 57. Plug in H equals 4000, make sure the result you get is 54. So that's a really important thing to do, not just to make sure you're getting the right answer, but working out that arithmetic will help you understand why point slope form works. So you're not just memorizing the formula, you're using a tool that you understand why it works and how it works. So that's an important thing. So I definitely recommend checking that this table agrees with this formula. All right, exercise 5 here. So yeah, cars are less efficient at higher speeds because the force of air resistance is greater at higher speeds. And in electric cars, this relationship is approximately linear at highway speeds. So, for example, a Tesla Model S has a range of 385 miles when driven at 40 miles per hour, and a range of 340 miles when driven at a speed of 50 miles per hour. So, let's get an equation for the range of a Model S driven at a speed of S miles per hour. So let's see. Well, let's make a little table where we have two values of S here and two values of R. We have S is 40 and R is 385 there. And when S is 50, R is 340. So using that, you can get the rate of change. And it's going to be, I'm going to do like R1 minus R2 and S1 minus S2. So that would be 340 minus 385 divided by 50 minus 40. And that is negative 45 miles is a change in the range in the top divided by a change of 10 miles per hour. So going 10 miles per hour here means that the total distance the car is going to be able to go is going to go down by 45 miles. And if you divide that, you're going to get negative 4.5. So this would be in miles per hour, which is a weird kind of number, a weird kind of unit. This is saying if you go 1 mile per hour faster, then the range that you can go is going to decrease by 4.5 miles. Okay, so that's the slope. You can use that now to get an equation. The equation is going to be r equals, we're going to do r0 plus the slope m times s minus s0. And the r0, s0 can be the values, it could be either these ones, or you could also use 50 and 340. And the slope, we just figured out, is negative 4.5. So this is going to be r equals 385 plus, or negative 4.5, or minus 4.5 times s minus 40. And that works. You could also, by the way, distribute the negative 4.5 into this, and you'd get r equals 385 minus 4.5 s, and then minus 4.5 times negative 40 is going to be negative 180, I think. Or plus 180, because it's a negative times a negative there. And then 385 plus 180 would be 565. So you could write it that way. Is maybe a little simpler. So this works. This one also works. Okay, now what is the range if you drive 82 miles per hour? So for part B, I'll do that one over here. We want to know what R is, so I'm leaving that as a variable, but I'm plugging in this value of S that they give, which is 82. And let's do that with a calculator really quick. We want to do 565. Oops. Get this into the frame. 565 minus 4.5 times 82 is 196. I should say miles. So yeah, driving a car faster is generally really bad for your fuel efficiency. So if you're trying to save gas, trying to do your part for climate change, it's usually better to drive your car more like 65, 70, maybe 75 if everybody else is going faster. That's why Prius drivers are always driving slow. I'm a Prius driver. I don't drive very fast. If you're wondering why, it's not because I'm not in a hurry. It's because I'm driving a Prius because I'm trying to fight climate change, and I'm also driving not too fast because I'm also trying to fight climate change. So yeah, it will generally use less gas to go slower. And this shows you about how much. Although it's a little different with regular gasoline cars. It's a little bit more complicated because you have the transmission, which makes things sort of more complicated. Anyways, that is this section. If you did all these exercises yourself, give yourself a big pat on the back. These are tough. And if you got stuck and then you got unstuck using the videos and then still did a lot of the work yourself, then you're also learning a lot from this too. So give yourself a pat on the back too. And I'll talk to you again in the C.1 videos.